Good afternoon. Thank you very much indeed for coming. So my task this afternoon is to take you on a bit of a tour of the solar system. For reasons of time, I have had to limit myself to planets and dwarf planets. If you have a particular enthusiasm for moons, I'm afraid I won't be talking about those, but you're welcome to ask questions at the end. One of the joyous things about being an astronomer just at the moment is that virtually everything that I'm going to tell you this afternoon has been discovered within our lifetimes. So as in the space age, we've had the opportunity to send spacecraft out to explore the solar system. We've learnt an enormous amount about what's out there. We've also discovered a whole load of things that we're not quite so clear about, so we've created a few mysteries for ourselves as well. And what I'll hopefully do as I go through this is highlight some of the things that we still don't understand about our local neighbourhood. So I'm going to start with Mercury and work my way out towards the edge of the solar system in the hope of giving it some sort of structure. And this is the first mission that was sent to Mercury. It was a NASA mission and called Mariner 10. And it's an example of how back in the mid-1970s, we didn't understand quite the environment that we were dealing with. So no sophisticated onboard computers on this spacecraft. So it had to rely for navigation on a star tracker, which was basically a telescope that was designed to take an image of the heavens around the spacecraft and find the star Canopus, which is bright, and lock onto it, and then use that as a way of navigating its way towards the planet Mercury. Now, one of the things NASA were concerned about was they were going towards Mercury. That was close to the sun. They were a little concerned that the spacecraft would get quite hot, so they provided it with a sun shield, which they thought would keep the electronics cool. That was a good idea. They then said to themselves, well, we're going to send radio signals up a waveguide to this antenna to beam the pictures that we take back to the Earth. Perhaps it would be a good idea if we painted that waveguide white so that it would reflect the sun's energy and not get too hot. And that was an example of how they didn't really understand the effects of the space environment on paint back then. We don't paint things that we send into space anymore because paint really doesn't enjoy the space environment. It tends to flake off. Now you can see what potentially happens here. The paint flakes off the waveguide and then starts drifting along beside the spacecraft, and eventually a paint flake drifts into the field of view of the star camera. Now it's very small, but it's very close to the camera and it's reflecting sunlight, so the camera, which is designed to find the brightest thing in its field, says, ooh, and starts to track the paint flakes instead of the star Canopus, which was a bit of a problem. Eventually, NASA realized what the problem was, and then they made a random maneuver to leave the cloud of paint flakes behind, and eventually they got to Mercury. And what they found when they got there, as you can see the picture on the right-hand side, is a very ancient surface. There are thousands and thousands of craters on the surface of Mercury, implying that it's a very ancient surface. There has been a long time for a lot of impacts to happen on the surface of Mercury. And I'll return to that sort of theme again later in the presentation. The number of craters you count are a good indication of the age of a surface. So we discovered a few things about Mercury that we didn't expect. We found that it has a magnetic field. I don't think many people thought that Mercury would still have some sort of liquid core that was actually allowing it to generate a magnetic field. We found an enormous impact feature called the Caloris Basin. And that's quite an interesting feature because what we think happened was there was a massive impact that created that crater, and the shock waves ran around the edge of Mercury until they met up again on the far side, at which point there was nowhere for the energy to go, and the energy basically just completely disturbed the surface of Mercury to the point where essentially the geologists just gave up and decided to call it weird terrain. Now, I'll just throw out one slight, sort of point to ponder. Does that same process happen on the Earth? So 65 million years ago, there was a very large impact that is supposed to have killed off the dinosaurs. That happened in the Yucatan Peninsula. So where's the opposite point on the Earth? Well, it turns out that's somewhere in the Indian Ocean, a bit south of where India is today, but almost exactly where India was 65 million years ago. And if you know your geology, you'll know there's a thing called the Deccan Traps, which are huge outpourings of lava that covered a large part of the Indian subcontinent, dated to about the same age, and at the point where India was 65 million years ago. Maybe that process happens here too. Now, a more recent mission to Mercury is called Messenger, and that spacecraft, another NASA mission, rather more sophisticated piece of kit with a much cleverer camera. So we're now looking at taking separate images in a number of different spectral bands, i.e. in a number of different color bands, and what that allows you to do is a much more sophisticated estimate of what the different materials are on the surface of Mercury. So some of them are thought to be impact features. Some of them are thought to be sort of volcanic type features where material came out of the interior of Mercury. And some of the areas, the stuff marked in blue on this picture, are still giving the geologists pause for thought. When we figure it out, we'll let you know. Now, one of the things that I find fascinating about these images from the Messenger spacecraft is that there are evidence of what I'm going to call volatiles on the surface. So volatiles, things like water, maybe carbon dioxide, anything that will turn into a gas when it warms up. You would have thought that Mercury, being relatively close to the sun, would have lost any of that sort of material a long time ago and would be completely depleted in volatiles. But the light-colored deposits on the surface that you can see here are very recent deposits. We can tell that because those deposits lie over the tops of the various impact features. So they must have been put there later. So geologically speaking, they're recent. And the best hypothesis for what's going on there is that when Mercury was formed, it was a molten ball of iron, to a first approximation, and there was the ability for that iron to accommodate a certain amount of hydrogen gas. And that over geological time, as Mercury is very slowly cooling down, the iron can't hold on to as much of that hydrogen. And so very slowly, Mercury is kind of fizzing hydrogen into the space environment and bringing with it whatever that light-colored deposit is. At least we think that's what's going on, but that's another mystery that we have to solve. We don't have a good idea at the moment of exactly what those deposits are made of. So moving on to Venus. So if you try observing Venus visually, it's a very challenging target, extraordinarily thick atmosphere. It's about 90 times the Earth's atmospheric pressure, and the temperature is enormous as well. You're looking at 480 degrees C, I think, on average. So it's not a very pleasant place to go. Most of the atmosphere is carbon dioxide. And as you can see from that picture on the screen, you can't see through the atmosphere in the visible part of the spectrum. That didn't deter the Russians. So the Russians were the first nation and still the only nation to ever land a spacecraft on the surface of Venus. A tricky thing to do, given the pressure and temperature. You'll notice that the spacecraft looks a bit like a pressure vessel. It's got a degree of spherical symmetry. A lot of the early Russian spacecraft were like that. If you picture Sputnik, it was also a ball. It was designed to be pressurized inside so that the electronics had a relatively benign environment to work in. And that spacecraft managed to get down to the surface. And it took the only pictures that we have of the surface of Venus. The version at the top of this slide is the picture that was put out by the Russians at the time. They were very proud of the fact that they'd managed to beat the Americans to land on the surface of Venus. The picture at the bottom is a more recently processed version of the same image, where they've corrected for the colour change that is involved with the light coming down through that very thick atmosphere. It's not very pleasant on the surface of Venus, but it's also not that funny mustardy yellow colour in reality, and the bottom picture shows what it would look like if you didn't have the atmospheric haze to deal with. The US have been to Venus. They haven't actually landed on the surface, but what they did do was put a spacecraft called Magellan in orbit around it. That spacecraft was deployed by the space shuttle and had a radar shown here that was able to send radio waves down to the surface, bounce the radio waves off the surface and receive the echoes, and essentially was the sort of satellite equivalent of a bat. So it was able to do radar imaging of the surface, and if you do that, you can essentially remove the clouds from Venus, which is what this image shows. So interesting surface. There aren't very many impact craters on Venus. Now, part of the reason for that is that there's a very thick atmosphere, but the biggest impactors potentially would still go straight through. So what that tells you, the lack of craters, is that Venus has a relatively young surface. And interestingly, the surface looks pretty much the same the whole planet over. And we think that about 500 million years ago, there was some resurfacing event on Venus. Maybe there was a major impact that dumped an enormous amount of energy into Venus and melted the whole of the surface. We're not quite sure. But whatever it was, all of the surface of Venus is only 500 million years old compared to a solar system lifetime of about 4.5 billion years. One of the other things that we've discovered from imaging Venus in this way is that there is evidence of volcanism everywhere. What's interesting about these features is they're somewhat reminiscent of the sort of volcanic features that you would see on Earth, but much, much bigger. So this is tens of kilometers long. It's an outflow from a volcano. And the reason it's so much bigger than the outflows from volcanoes on the Earth, despite the fact that Venus is a similar sized body to the Earth and has similar gravity, is that the temperature is so much higher that the rocks are much less viscous and the lava essentially flows more like water than the sort of lava we're familiar with on the surface of the Earth. Now, we haven't necessarily caught Venus in the process of having a volcanic eruption. It's a little tricky to do with all that atmosphere in the way. The European Space Agency has sent a mission and put it in orbit around Venus as well. That mission had an infrared camera, which was able to look in the heat bands, and they found some things that look rather like volcanoes, which appear to be hot at the top. So that's a pretty good indication that they genuinely are volcanoes and could erupt at some point. And there are some observations, such as this bright spot that was seen in Venus's atmosphere. So it's a transient feature. It appeared for a while in Earth-based telescopes and then disappeared again. And you wonder, well, what was that? Well, it's possible it was a volcanic eruption down on the surface, throwing a whole load of different chemicals into the atmosphere of Venus at that particular location, which interacted differently with the sunlight and made Venus look a little bit different in terms of colour in that particular location. But we still await the first conclusive evidence of a volcano actually erupting on Venus. One of the things that's really puzzled the scientists is the fact that in the gap between the American Magellan mission and the Venus Express mission, the winds and the rotation of Venus appear to have changed significantly. The winds have got a lot faster. They've gone from, on average, 300 kilometers an hour to 400 kilometers an hour. And the rotation of Venus, which is extremely slow, appears to have changed by about 6.5 minutes in the same sort of period of time, about 20 years, which is really quite astonishing. I mean, if you think about the Earth, it's about the same size a planet as Venus. Our rotation changes almost imperceptibly over that sort of time. You've probably heard of us adding a leap second occasionally. That leap second is added to account for the fact that the Earth is very slowly spinning down. but it would appear that Venus can change its rotation rate by 6.5 minutes in the same time, which implies there's some really weird and interesting interaction going on with its atmosphere that we don't understand at the moment. So moving on to Mars, I'm going to skip over the Earth because we're already here. So one of the first major missions to Mars, there were a few missions that sort of flew past and took images as they whizzed by. But the first major image, significant mission, was the one that Carl Sagan, who was mentioned in the introduction, was much involved with. So it was the Viking landers. The landers actually inside this entry shroud. So this part of the spacecraft detached. This bit stayed in orbit to relay the pictures back from this lander that's folded up inside here. And when they landed, they used this scoop to dig a trench in the surface, scoop up a bit of Martian soil, and deploy it into essentially a chemistry laboratory on the lander. And they attempted to spot Martian microbes in the soil. They essentially provided nutrients that they thought might feed a bacteria. They saw a reaction inside their chemistry lab. There is still a debate even today about whether they actually detected some sort of microbial life in the surface. It's a very long debate. I don't have time to reiterate it all here, but there are also some very active chemicals in the surface of Mars that might also have created the reaction that they saw. So it's not entirely clear. Also, bacteria are surprisingly stubborn things. They can withstand all sorts of exposure to the space environment. Although they tried to clean the Viking spacecraft before they sent them, it's possible that there was still some contamination from some Earth bacteria in the experiment somewhere, and that when they actually deposited the nutrients in the Martian soil, all they did was feed some Earth bacteria that they had taken with them, and that debate continues now. One of the reasons why I'm a big fan of robotic exploration rather than manned exploration is that there are so many different places on Mars that I would love to send a robot to. There are all sorts of different terrain, from polar caps where you can find water ice and carbon dioxide ice. There are all sorts of dunes and sand-based features. There's all sorts of really, really interesting stuff on Mars, and this slide just sort of shows some of the variety of different places that you can go and visit. So unlike Venus, which has a very uniform surface, Mars is very different. Some of Mars's surface is covered in craters, implying it's quite old. Some of the northern hemisphere of Mars has almost no craters, and that's part of the clue to the fact that there may once have been an ocean around the North Pole of Mars. We've managed with European spacecraft, a spacecraft called Mars Express this time rather than Venus Express, to catch transient features on the surface of Mars. So these are avalanches. We think they're created by carbon dioxide frost. As the seasons change on Mars, just like there are seasons on the Earth, the temperature of the surface heats up, and some of the carbon dioxide essentially warms up enough to burst out of the surface and create an avalanche, which you can see in the pictures here. These are two different avalanches, and the fact that we've been able to image more than one of these very transient events implies that they're happening relatively frequently. The most comprehensive mission that's been sent to the surface so far is a mission that's still working. It was sent by NASA, the Curiosity rover. Really complicated landing sequence involving parachutes and heat shields initially, and then there's this sort of hovering deployment device which winches down the lander, which is about the size of a Mini, onto the surface. But now, within our lifetimes, we've gone from the pictures of Mars that we had at the beginning of the space age, which were based on Earth-based telescopes, where the pixel resolution, if you like, was hundreds of kilometers across, to being able to take close-up pictures of rocks that are really, really detailed. And I think that's just an amazing leap forward in terms of our understanding. Now, one of the things that rover was intended to try and answer was there ever liquid water on the surface of Mars? Lots of speculation about whether there was or whether there wasn't. This first image from its camera pretty much proves it. So I hope you can see that there's quite a lot of evidence in these hills of layering. Okay, so that's like sedimentary layers on the Earth. They are almost certainly laid down in the presence and absence of water, but the fact that there are layers at all is almost a dead giveaway to a geologist that there was definitely water here once, which is an interesting situation, as I'll explain in a moment. That rover, as I mentioned, has been able to take some very close-up pictures, including this thing, which looks like almost like a little flower. Now, it's almost certainly inorganic. It's probably some form of crystal growth. Mars has a very, very thin atmosphere, so it's almost like growing crystals in a vacuum. We don't see the same conditions on the Earth, obviously. So exactly what that is, we're not sure, because we don't see the equivalent on the surface of our own planet. But the fact that it's there at all is really interesting, I think. Now, what's got NASA extremely excited is the fact that both from their orbiting missions and also from the rovers down on the surface, there's quite a lot of evidence now that there is methane in the atmosphere of Mars. Methane is produced on the Earth largely either by volcanic activity or by biological activity. And we think that most of the volcanic activity on Mars stopped a very long time ago. There are areas of volcanoes on the surface of Mars. In fact, the biggest volcano in the solar system, Mons Olympus, is on Mars. But we think all of that volcanic activity stopped a long time ago. So the fact that we see methane today and we see it in a sort of seasonal fashion rather than sort of like continuously throughout the Martian year does sort of suggest that it's seasonal, and that just like plants on the Earth grow in the spring and summer and then lose their leaves in the winter and the autumn, that there is seasonal activity, perhaps in biological activity on Mars. I had the good fortune to have dinner with Jim Green, who's the chief scientist at NASA, a couple of weeks ago. He wasn't exactly saying, we've found life on Mars, but when asked, sort of smiled and said, we find increasing amounts of evidence. And I think the situation NASA finds itself in is there's a lot of scientists at NASA who think they've got some very compelling evidence for essentially bacterial sort of life forms on Mars. And that they're, an extraordinary claim, we've found life on Mars, needs extraordinary evidence to prove it. So they're not going public yet. I think they want to build the case even further. But there are some interesting facts about this methane. For example, the methane disappears very quickly, and that's a surprise. You would expect the methane to hang around for some tens of years before being broken down by the ultraviolet light. So if you find methane for a while as part of some sort of burst of activity and then it disappears again, that sort of implies that there's something eating the methane, maybe. The final thing I want to say on Mars is, did it once have an ocean? So as I mentioned, if you artificially flood a map of Mars with water, you find that the water tends to congregate around the northern hemisphere. Now, Mars is further from the sun than we are, and it's a smaller body than we are. So at the formation of the solar system, it's possible that Mars would have cooled down to the point where it could have had an ocean, liquid water on its surface, before the Earth did. And then it's possible that life got started in that ocean, and then there would have been impacts, and we see a lot of impact craters on Mars. So we know that Martian meteorites have been found on the Earth, and we know that bacteria are very stubborn things. So is it possible that bacterial life from the oceans of Mars got transported to the Earth in a meteorite, landed on the Earth, and then said, it's not so bad here, maybe I'll evolve into us? It's just possible we're all Martians. Now, I expect you were expecting to see Jupiter next, but I'm going to stick the dwarf planet as it's recently been promoted to. So Ceres started off its life as a planet when it was first discovered in 1801. It then got relegated to being an asteroid, and now it's been promoted again to being a dwarf planet. Now, what's interesting about Ceres, it's got a very dark surface in general. It's been exposed, as you can see, lots of impact craters, pretty old surface, you would think. And then you find this rather interesting bright feature. Bright features not covered in lots of solar system dust. That means that bright feature is recent. And if you zoom in, you see potential evidence of eruptive geysers. Stuff is coming out of the surface. And this is what you get if you get the highest resolution images. This is taken by the spacecraft called Dawn that went into orbit around Ceres a while ago, and I think is still operating in orbit around Ceres. And you can see that there is material, very young material on the surface. There are salts present there. We think it's very briny sort of water being squeezed out of the surface, but it's a real surprise, A, to find that there's anything fluid there at all, and you wonder what process, what energy source is providing the energy to squeeze that stuff out of the interior of the body. Don't know. There are also mountains on Ceres. So this is a picture looking down on the top of a cryovolcano, an ice volcano. And this is what it looks like side on. Now, I don't know whether you're interested in that, but as somebody who builds spacecraft, I'm looking at that large pile of ice and thinking, that's my fuel depot for when I want to go somewhere else in the solar system. It's not hard to find, is it? There's a massive great pile of it on the surface, and because Ceres is a relatively small body, it's much easier to get down onto Ceres and get back off again than it would be to go and, say, mine the polar caps of Mars. So this is an exciting place from a rocket scientist's point of view. Now you get Jupiter. The quality of the images that we're getting on Jupiter now are immense. The Great Red Spot, if you haven't heard, for scale is bigger than the planet Earth and has been observed, continuously to be operating ever since Jupiter was first looked at through a telescope by Galileo. So we're aware that it's a very long-lived feature. You'll notice that the banding, the horizontal banding, is the sort of stuff that occurs at moderate latitudes. And we learned a lot about Jupiter from this mission, but it's another example of where space exploration doesn't always quite go the way you hope. So this is what the spacecraft was supposed to look like. This is a sort of an umbrella-like antenna that was folded up during launch and was supposed to unfold a bit like an umbrella, but it was actually like a regular terrestrial umbrella. They never unfold properly when you need them to. So some of the ribs of this antenna got stuck here, and it never unfolded properly. So they had to use a separate antenna that was just used to send engineering data about the spacecraft back. They had to use that much smaller, much less capable antenna to dribble all the data back from this spacecraft. But nevertheless, it told us a lot. When it arrived at Jupiter, it dropped a probe into Jupiter's atmosphere, detected an awful lot of lightning, didn't detect much water, but they took a picture of Jupiter at the point where the probe was entering Jupiter's atmosphere, and it dropped into this dark region here, which we think is a region where essentially there are no water clouds. And so the probe didn't detect water just because it missed. And we think that some of these other different color bands might well have had quite a lot more water tied up in them. Now, the spacecraft that's in orbit around Jupiter at the moment is called Juno. Notice that it looks a little different to some of the deep space missions that you may have seen in that it's got solar panels. This is the first spacecraft to go beyond Mars that's powered by solar panels. All the deep space missions that we've done before have had things called radioisotope thermal generators, basically a radioactive heat source that decays, generates heat, and that's turned into electricity to power the spacecraft. But the quality of solar panels has increased to the point where you can now go all that distance out of Jupiter and go that far away from the sun and still generate enough power with solar panels. So this mission is deliberately designed to go over the poles of Jupiter and give us a sense of what the poles look like. And interestingly, they're very, very different from the banded structure that you see at more moderate latitudes. There's all sorts of cyclones and interesting things going on at the pole. That mission is still running, and expect more details from it soon. Moving on to Saturn, I find this absolutely fascinating. You see the rings, and they're really, really impressive, but they are only a couple of 100 meters top to bottom. Thousands of kilometers side to side, 200 meters top to bottom. It's now thought that as well as gravity affecting the motion of those particles, that also there is electrostatic forces. Essentially, the particles in the rings acquire essentially a static charge from the solar wind, and then all the particles want to, because they're all at the same charge, they all want to stand at arm's length to one another because they're all like charges repelling. You get storms in the atmosphere of Saturn from time to time in the summer months, because Saturn has seasons too. And a lot of what we've learned about Saturn is from this mission called Cassini, launched after Galileo, and notice that NASA changed their strategy for antennas. No unfurlable umbrella-like thing this time, fixed dish. Don't have to worry about deployments messing up your mission on this one. I find this picture rather amusing. This was a joint NASA-European mission, but this is the American picture of the mission. The European contribution is this lander that was dropped onto the moon Titan, and as you can see, the Americans didn't really sort of show it off to the best advantage. So one of the brilliant things they did with this mission was they went, when the spacecraft was sort of in eclipse behind Saturn, and the sun was immediately behind Saturn, they took an image looking back towards the sun, and necessarily, because the sun is somewhere behind the disk here, all the interior planets are pretty much in that direction from the point of view of Saturn. And I don't think it really shows up on this projector, but there are some little bright points which are the interior planets. This is really weird. So Saturn is quite significantly out of round. It's about 10% oblate, so the pole-to-pole distance is much less than the equatorial radius. But around the poles of Saturn, there is a hexagon. Now, it's a rotating oblate spheroid. How do you get straight lines on a spherical, near-spherical rotating body? If you know the answer to that, please tell me, because I'd love to know. So the deep space stuff has largely been done by Voyager 2. It's the only spacecraft that has been to Uranus and Neptune. Flybys in both cases, so brief opportunities to collect data. This is a more recent ground-based image of Uranus showing the one bright ring that it has around it. It doesn't have a sort of huge ring system like Saturn. According to the textbooks, that ring system was discovered in 1977. I've been doing some research recently, and I think William Herschel spotted that ring in 1789, but that's a different lecture. So one of the things that Voyager discovered is that Uranus has a really weird magnetic field. So on the Earth, as you're aware, we think the dynamo theory accounts for our magnetic field, and the magnetic field has to line up with the spin axis of the Earth. It's not like that on Uranus. There is a 60-degree angle between the magnetic axis and the spin axis. And the spin axis is weird. Most of the planets rotate with their spin axes sort of largely pointing up out of the orbit plane that they're in, whereas Uranus's spin axis is almost in the plane of the solar system. Can't explain that very well either. Might have been hit by something at some point, but if so, what hit it? And where is that thing now? Neptune turned out to be interesting in that Uranus was almost a completely bland disk. There's a lot more weather going on Neptune. Great dark spot, which is a fairly transient feature, but it's very large. These light bits are clouds that whistle around Neptune very rapidly, hundreds of kilometers an hour. Lots and lots of activity that we didn't see at Uranus. But Neptune's further away from the sun, and it's colder, and it should be less active. Don't understand that either. And finally, just to talk a little bit about going to Pluto. So this is the New Horizons mission. It took nearly 10 years to reach Pluto. NASA didn't want to do this mission. Congress mandated it because Pluto was discovered by an American, a place called Flagstaff in Arizona. And when the International Astronomical Union decided that Pluto was going to be relegated to the status of dwarf planet rather than true planet, the people in Arizona took exception to that. Sorry, it's New Mexico. It's Flagstaff in New Mexico. They decided that they were going to pass a law. And if you go out there and you visit Flagstaff, be aware that it is the law there that Pluto is a planet. No, it really is. You ask them. So this is what New Horizons found on Pluto, and again, utterly fascinating. Lots of craters in this sort of region, but this bright heart feature, as it's known, is almost completely devoid of craters. There is evidence of cryovolcanism, i.e. ice volcanoes, on Pluto too. Again, the question, what the hell is providing the energy for that? And if you look very closely at that smooth area, it looks very much as if you've got nitrogen glaciers flowing across the surface. Well, where's the energy coming from to drive them around? And if you look really close up, you can see it looks as if there's some sort of slow rolling sort of, it's a bit like boiling porridge or something, if you've seen the way that porridge behaves in a pan. Similar sort of thing, except this is much colder and it's nitrogen that's doing it. But no impact craters at all, a very young feature. And this is the final picture that New Horizons took as it sped away from Pluto looking back. And notice the atmospheric layering here. There's all sorts of different species of stuff in Pluto's atmosphere. We're still trying to work out what the different layers are, but it's a sort of fitting farewell to the solar system, if you like. And at that point, I'd better stop and take some questions. Thank you very much.
Thank you. This is a very basic question from somebody that knows nothing about science.
That'll make it more embarrassing when I can't answer it.
How do you know that the striations would be made by water? And how do you know that you say there's water there or nitrogen or what rocks they are and what chemicals? How do you know that?
Yes, so it's a good question, and I have to admit that you're repeating a question that I asked one of my university lecturers many moons ago. So I said, how do you know for sure it was water rather than, say, liquid carbon dioxide or something? So the answer to that question is to do with the pressures that were likely to be around and the commonness of oceans made of water compared to oceans made of anything else. At least that's the general theory, although you look at Titan, the moon that I briefly mentioned, going around Saturn, that's got liquid on its surface, but the liquid is liquid methane. So just as the Earth is at the triple point of water, so you can have ice and steam and water on the surface of the Earth, you can have the same three phases, gas, solid and liquid, of methane on Titan. So the probability is high based on the chemicals that have been found in the rocks that have been analysed by the rovers. So the rovers have looked at some of the chemicals, and I'm not enough of a geologist to be able to name them for you, but there are some chemicals that they've essentially dug up and looked at on Mars that are only formed in the presence of water as opposed to carbon dioxide or anything else. So there's good evidence that there was definitely water. There might have been other things. I mean, there's certainly carbon dioxide in the atmosphere of Mars and bound up in its polar caps, so maybe at some point there might have also been carbon dioxide liquid on the surface. But
if Venus is slowing down so quickly, what's happening to the angular momentum?
Well, that's what we think is speeding up the atmosphere. So there's an exchange of energy between the rotation of the planet and the speed of the winds, and exactly how that works we're not clear, because it's not a process that we see on the Earth. The Earth's atmosphere is nowhere near as dense. You know, it's sort of like 2 orders of magnitude more dense on Venus. So presumably there's some way of exchanging energy between the two, but you can't account for the speeding up of the winds unless you get energy from somewhere, and at the moment it's assumed that energy is being stolen from the rotation of the planet, but a full explanation is still awaited.
So what happens when it stops?
Yeah, well, that's one of the interesting things. You can get captured rotation, and it's possible. Mercury is almost in captured rotation. A weird thing about Mercury is that a year on Mercury is only half the length of a day on Mercury. So it takes Mercury 88 days to go around the sun, and a day from sunrise to sunrise on Mercury is 176 days. It's almost captured, and it could be that Venus will end up the same way.
Can you say how big Ceres is, and therefore how big that ice mountain is compared to anything
just
else?
over 900 kilometres in diameter. About 1/6 of the size of Mars, or perhaps 1/12 the diameter of the Earth. So, if the Earth is like that, Ceres is like that.
And the mountain?
Oh, sorry, the mountain. I think that was on the slide. I think it's about 4 kilometres high or something like that. I mean, it's a surprisingly large lump of ice to be sat on the surface.
Could you tell me what shape the orbit of Ceres is, and what defines a dwarf planet?
Right. So the shape of the orbit is pretty much a circle, I think. Some of the asteroids are more elliptical, but I think Ceres has a fairly circular orbit, sort of midway, sort of between Mars and Jupiter. I don't know if you're interested, you could look up a thing called Bode's law, which tries to use a rather sort of noddy mathematical formula to predict the positions of the planets. And they used to think that they had a gap in that law between Mars and Jupiter, and then they found Ceres and it seemed to fit the bill. Definition of dwarf planet is enormously controversial, as indeed the definition of a planet. This is what got the people in the States so steamed up when the International Astronomical Union decided to redefine Pluto. So according to the IAU, a planet is one that has an orbit around the sun, and that it's large enough that gravity has pulled it into a sphere. That's what they actually wrote. They eventually backtracked and said hydrostatic equilibrium, because they realized that Saturn wasn't a sphere, and they would just ruled out Saturn as a planet. That was embarrassing. And then they said something that's got them into an enormous amount of trouble, which they said, it has to have cleared its orbit of other bodies. So, major planets that, sort of have no other major planets crossing their orbits are good. But if you have, in the case of Ceres, lots of other asteroids sort of crossing, it's not necessarily the dominant gravitational force in its orbit, and that was used as some really dodgy but very unscientific, because not unreasonably you might be sitting there thinking, well, what does cleared its orbit mean, and by how much? And if you've got a moon going around your planet, sometimes that moon's going to cross your orbit. Have you cleared your orbit? Embarrassingly, Jupiter has 2 large groups of asteroids that are 60 degrees ahead of Jupiter and 60 degrees behind it, called the Trojan asteroids. They're there for gravitational reasons. They will be for the lifetime of the solar system, as far as we know. So Jupiter hasn't cleared its orbit because it's got loads and loads of asteroids sharing its orbit for gravitational reasons. But the IAU seem to have overlooked that fact. So Jupiter's not a planet either by that definition. It's a really rubbish definition, and I can't offer you a better one, I'm afraid.
Well, thanks so much, Stuart. I'm really sorry, but we are overrunning very slightly. Stuart, are you going to be hanging around for the tea break?
Yeah, absolutely. So if you want questions later, I'm happy to help.
Please do see the man in the astronomical waistcoat. But for the time being, can we say thank you very much to Stuart Eves.
Sure.